Hi, today I'm going to be teaching AS level physical chemistry. I'm doing the AQA specification and I'm on the topic bonding. Today I'm going to be doing 3.4, which is electronegativity. So what electronegativity is a measure of the atom's ability to attract the shared electron pair in a covalent bond towards itself. Chlorine is the most electronegative element, followed by oxygen, nitrogen and chlorine. And this is measured on the Pauling scale, where a higher value means more electronegative. So fluorine, which is the most electronegative element, has a value of 4.0. There are multiple factors that affect electronegativity, one of them being atomic radius, and this means that smaller atoms are more electronegative because their electrons are closer to the nucleus, resulting in a stronger electrostatic attraction. This means that the closer they are together, the more the nucleus can draw in electrons. Another factor is nuclear charge, and this means that a higher positive charge on the nucleus increases the strength of the electrostatic attraction between the nucleus and the electrons. This makes an atom more electronegative. So the stronger positive charge in the nucleus, it can bond, means the bond between the positive nucleus and the negative electrons is stronger. Shielding is the third factor. Shielding is another factor that affects electronegativity. And it means that electrons in inner shields can weaken the electrostatic attraction between the nucleus and the outer shell electrons, reducing electronegativity. So this means that the inner shields between the nucleus and the outermost electrons act as like a barrier which block the bond. And okay, so there are trends in electronegativity across the periodic table. So, for example, across periods there is an increase in electronegativity. This is because the nuclear charge increases, pulling the electrons closer and decreasing the atomic radius, resulting in a smaller electrostatic attraction. No. So there are trends in electronegativity across the periodic table. For example, across periods there's an increase in electronegativity. This is because the nuclear charge increases, pulling the electrons closer. This then decreases the atomic radius and creates a stronger electrostatic attraction between the nucleus and the electrons on the shell. Whereas down groups, there is a decrease in electronegativity because despite the increase in nuclear charge, there is also an equal increase in shells, and therefore that increases the atomic radius and shielding. And this means that the inner shell of whereas down groups, there is a decrease in electronegativity. This is because despite the fact that there is an increase in nuclear charge down the group, there is an equal increase in more electron shields, and therefore shielding occurs. And this also increases the atomic radius. So this weakens the electrostatic attraction between the nucleus and the outer electrons, and therefore causes a decrease in electronegativity. Now I'm going to talk about polar bonds. So the differences in electronegativity between bonded atoms can cause polar bonds. So the bonded electrons are more strongly attracted to the more electronegative atom. This creates an unequal sharing of electrons and makes the bond polar. Polar bonds have a permanent electric dipole, which is a separation of positive and negative charges within a polar covalent bond, or polar molecule. The bigger the difference in electronegativity, the more polar the bond. So, for example, here you see an example of a polar bond, HCl, and you see there's a symbol there, which is delta. So delta means slightly, because they're not like ions, they're not completely positive and completely negative. They're slightly positive and slightly negative. So we refer to that as delta. So in this polar bond, HCl, hydrogen is delta plus because it's less electronegative, and chlorine is delta minus because it's more electronegative. And therefore the electrons are drawn towards the chlorine, which is an unequal sharing. Whereas a non-polar bond, two hydrogens, H2, and that's because they have the exact same electronegativity, and bonds between multiple of the same atom or atoms with similar electronegativity are non-polar. So the total charge is also unevenly distributed in polar molecules, and the overall polarity depends on a molecule's 3D arrangement. See here, here's an example of CCl4, and carbon is positive, delta positive, whereas all of the chlorines are delta negative. And they basically balance out, which makes it a non-polar molecule despite the individual bonds being polar. Whereas here you have CHCl3, which is a polar molecule because both carbon and hydrogen are delta positive, whereas the three chlorines are delta negative and they don't cancel out. So to figure out whether a bond is polar or non-polar, you need to visualize the 3D structure and assess if the individual bond dipoles cancel each other out. Now, an importance of electronegativity is that it can predict bond type. So here is a table where you see the differences in electronegativity. So you see that if it's less than 1, it's a non-polar covalent bond, typically. If it's between 1 and 2, it's a polar covalent. And if it's greater than 2, it's an ionic bond. Now, most compounds fall somewhere between these extremes, and therefore they exhibit a mix of ionic and covalent character, depending on the difference in electronegativity between the bonded atoms. And that's all you have to know about electronegativity. Thanks for watching. Bye.